So let's get started with this. This is the fourth segment of our lecture in this section 2.3. Okay, we're going to have to do what we call rationalize the numerator. Now, you have worked through a typical topic in Algebra 1 and Algebra 2 is to rationalize the denominator. We're going to do the numerator instead. This means we want to make the numerator a rational quantity. In other words, we're not going to have any square roots up there. Okay, so to do this, we're going to have to, let's see, we start with x, limit as x approaches 0. And we're going to have to use an item for this known as the conjugate. If you recall, the conjugate is a plus b, the quantity a minus b is always going to be the format of our conjugates, where we are going to use the same item, but we're going to change the sign in here. Okay, so I'm going to multiply this with the square root of 3 plus x plus the square root of 3. But now I've got to remember, I don't want to change the value of the original function. Only way I can do that is if I multiply by a factor of 1, so I'm going to have to multiply a fraction whose denominator is the same as the numerator. Keep in mind, we have to keep writing the limit as x approaches 0 until we use direct substitution. Okay, so in our numerator now, if we think of these as two binomials, we're going to use the FOIL process. So we're going to use FOIL, first, outside, inside, last. So the first terms are going to be 3 plus x. The square root times the square root is the square, or the square of the square root is just 3 plus x, minus the square root of negative 3 times the square root, the square root of 3 times the square root of 3, which is going to be 3, divided by x times the square root of 3 plus x plus the square root of 3. Doing the same thing you did in high school with the rationalizing the denominator, we're just going to rationalize the numerator. Okay, we still are not able to use direct substitution because this would become 0, which would of course affect the entire denominator. But if we take a look at the next step, the limit as x approaches 0, and we have 3 plus x minus 3, that becomes x. There's the x down there. We have the square root of 3 plus x plus the square root of 3. At this point, those factors of x cancel. What we're left with then is the limit as x approaches 0 of 1 divided by the square root of 3 plus x plus the square root of 3. Now, at this point, can we substitute 0 in for x? And the answer is yes. So, the next step, I do not write the limit notation because I am going to take direct substitution. So I am taking the limit when I make that substitution. And I end up with 1 divided by 2, the square root of 3. Okay, let's take a look at this on the Inspire. Make sure that we have a correct problem, a correct answer here. So I'm going to do a Control Home, insert a new problem, and it's going to be a calculator page. all I want to do is to go back to this problem and just take the limit of that. Okay, so I am going to find my template for the limit and press enter. And I have as x approaches 0, and I have a fraction, and I've got to get the square root of 3 plus x. Make sure I move outside of that square root sign, minus the square root of 3 divided by x. What we're doing now, we're not getting the answer, we're going to check our answer. So we press enter, and our answer is the square root of 3 divided by 6. That does not sound familiar. We had 1 divided by 2, the square root of 3. Now, I'm sure that you've been told you can never leave a radical denominator, and with technology, my question is, why not? I can do this with my calculator, my page, and be just fine. So let's try something here. What we're going to do is take our answer, 1 divided by 2, the square root of 3, and compare it to the answer that the Inspire has. Now, should we be able to use our algebra and verify that our answer is equivalent to this? Absolutely. But let's look at a way that we can use our Inspires to help us check our answers. So let's go up and capture that, press enter, find the equal sign, and now we're going to type in 1 divided by 2, the square root of 3. So get a fraction, 1 divided by, there we go, divide by 2 times the square root of 3. Now, if these two expressions have the same value, you're going to see the word true come up. If anything else happens, we're going to assume that there is an error someplace. So we press enter, and it's one of my favorite 4-letter words there, the word true. So our answer is equivalent to the answer, the square root of 3 divided by 6. I accept this answer for me because I know technology is in our lives and we're okay with using it for this work. I'm perfectly fine. Have you demonstrated your ability to rationalize the denominator? Yes, by rationalizing the numerator. Let's go back and take a look at this though. There are some very important pieces that you need to have in here. One is you need to show me the notation of the type of problem we're working with every step along the way until when? Absolutely. Until we've actually used direct substitution. When we use direct substitution, we no longer are allowed to use that notation. If you put that notation here, it's incorrect. So you have to know when to use it and when not. And we're going to use it until we use direct substitution. Okay, let's move on. Our next problem. A little complicated in looks. Not really that much difficult from what we're able to do. But again, the packaging of the math we look at can sometimes throw us. Okay, we don't have x, we have delta x. Delta x stands for the difference between input values. So the difference between two input values in this problem is going to be approaching 0. In other words, two input values are moving closer and closer and closer to each other until there's almost no difference between those input values. We have a quotient, and we have the difference of perfect cubes. Now, you may or may not know how to expand the difference of two perfect cubes. And without going into a lot of detail, suffice it to say that if we use Pascal's triangle, if you know what Pascal's triangle is, you can find that out If you don't, you can use your Inspire to expand this, and we'll look at that in just a moment. The other way to do it would be to take x plus delta x times x plus delta x, and then x times delta x. Okay. Okay, so let's go to our Inspires and do exactly what I was talking about. Let's go to Menu, go to Algebra, and go down here to what's called Expand. We're going to expand the cube of a binomial, so put another set of parentheses in there. And we're not going to use delta x, we're going to use something else. So we'll say x plus y, and we're going to raise that to the third power. We have to have the set of brackets just to encase the quantity we're going to expand, and then the other one is because we have a binomial. And we're going to expand that, and we have x cubed plus 3x squared delta x in our case, plus 3x delta x squared plus delta x cubed. So that's one way you can expand that. So let's see, we've got x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed, that's this part, minus x cubed, all of it divided by delta x. Let's stop one moment and talk, why can't we use direct substitution? Absolutely, it would give us a zero denominator. Okay, so we have to do something else. Okay, at this point, when we see all of this, let's see, we've got an x cubed and an x cubed. One's positive, one's negative. It's going to cancel out. Something else that I see, I have a delta x term, a delta x squared term, and a delta x cubed term. So I'm going to write the limit as delta x approaches 0, and I'm going to factor out a delta x from each term. Divided by delta x. Why? Well, look at what we just wrote. The reason I couldn't use direct substitution is because I had delta x in the denominator and I cannot replace it with 0. At this point, when I factor out a delta x, that problem goes away. Again, this is why we want to be able to rewrite our work and be able to find other functions equivalent to the original, except at the point where delta x is 0. Now, I could go through and rewrite this again, but as a lazy mathematician, and I know you are not into writing this multiple times, since the delta x is not there, I am left with this. If I want to ask myself, can I use delta x? Can I use 0 for delta x? And the answer is absolutely, and I come up with 3x squared. Okay, so the limit as delta x approaches 0 of this quotient, we call this a difference quotient. We're going to be talking about that when we get into the chapter 3. A difference quotient, that's exactly what that is. As we have delta x approach 0, that is 3x squared. Now, for those of you who've had calculus before, do you recognize this? Have you recognized what we're getting to? We're not going to give it away just yet, but this is very much connected to the work we do in chapter 3. Okay. We're going to look at another problem very similar to this, except that we don't have, in this problem we had x plus delta x. Here we have f of x plus delta x, a little more abstract, still a difference quotient, and we will do that in the next segment.